Hello, my name is Tay Ritzie, and I'll be talking about encoding material empathy, a review of physical materials and digital geometries. The statement above was Zaha Hadid's response in a 2014 interview with The Guardian regarding the death of 500 Indian and 382 Nepalese migrant workers who died in preparation of the 2022 World Cup in Qatar. While it has been clarified that none of the deaths occurred in the late architect's construction site, the declaration for architects to be unassociated with exploitative labor questions the extent of power and ethical considerations adopted by the architect in the construction industry. Extravagant forms conceived through the digital environments by contemporary architects like Zaha Hadid and Frank Gehry are only realized through the support of construction labor. While the digital environment is becoming increasingly sophisticated, the construction industry remains as one of the most manual industries, second only to agriculture. The research looks towards the development of digital geometries within digital environments and physical materials used in construction to understand the cause of discrepancies between the two. All digital geometries are not real until they are constructed, and each digital geometry represents a digital version of its physical self. Considering the opposing states of digital environment industry and the construction industry, are we working with the same physical materials and digital geometries from formulation to fabrication? Physical materials refer to the media that craftspersons work with in the fabrication stages, while digital geometries refer to the media that architects work with in the formulation stages. This is inclusive of splines, triangulated mesh, and dynamic vectors. While the digital environment offers the possibility to encode digital geometries as desired, this is not the case with physical materials. Physical materials embody their own material complexity and are embedded within larger networks of supply chains and requirements of labor skills. This unaccommodating perception of material behavior results in highly resource-intensive construction practices. To understand the trajectory of digital environment and its contrasting development against construction processes, we must trace past its history within the scope of the architect and identify the point at which architecture first branched away from the scope of the master builder. This division was set forth by the revolutionary shift in worldview from a foundation of divine supremacy to an anthropocentric reality in the 16th century, as written by Maria Vojatsky in Non-Human Creativity. The master builder of the past has split into two separate professions today. The architect, using cognitive abilities to formulate ideas remote from physical materials, and the craftsperson, using sensors and working with physical materials to formulate resultant artifacts. As architects were granted exclusive authorship of the creative process, the following trajectories of physical materials were aimed to fulfill a supportive role, manipulating materials to morph according to the architect's assumptions. It can be observed that the three periods of material history demarcated by Cyril Stanley Smith pursued an understanding of material behavior to domesticate the complexity of material behavior and diminish its vitality. The perception of material as an imperative subject was displaced through empirical research that quantified complex material behavior into domesticated avenues of control. In pursuit of unbounded creativity, the development of cognitive formulation was complemented by the establishment of digital environments. Andrew Weed defines the digital environment as a dimensioned virtualized space, yet it offered a habitable domain that could facilitate cognitive imagination without dependency on physical reality. Sutherland's sketchpad thesis in the 1960s enabled the first direct interface between humans and machines, taking in cognitive input and publishing it as a geometry into the digital realm that could be scaled and manipulated as desired using its encoded values. Instinctive forms of splines could be more accurately expressed through these new avenues of value control offered by digital geometries. Digital geometries refer to technologically enabled geometries with multivariable functions and encoded intelligence, and can take on the form of points, lines, surfaces, three-dimensional meshes, or vectors. In the 1970s, Charles Eastman's building description system extended the collaborative aspect of the digital environment through extending the list of encodable information of building elements. Developing a foundation of shape, list of information, and position within a digital model, elements constructed in BDS could converge fragments of reality into the digital environment. Today, BDS has evolved to the BEAM system that has been recognized for establishing a collaborative foundation with different professions within the built environment, but also often criticized for its limitation for creative formulation, as every digital geometry had to be attributed to an existing architectural element within the software. In the 1980s, Stephen Wolfram gave new life to digital geometries by defining the potential of cellular automata. Through encoding particle genes facilitated by computational processes, digital geometries could now calculate predictions more accurately than human inference ever could. It is in this trend of technological development that digital geometries evolved into autonomous digital geometries, encompassing its own intelligence unreplaceable by humans. While physical materials were increasingly domesticated, with the discovery that material properties can be defined by altering the outer valence of an atom, digital geometries became increasingly autonomous through attributing more encoded information upon its creation. This trajectory of digital geometries disrupted the human-centric reality it was founded upon and supported the rise of autonomous digital geometries, further straining the relationship of formulation against fabrication that is bounded to reality. The dialectic of enlightenment, the leading members of the Frankfurt School argued that instrumentality is a form of domination, that controlling objects violates their integrity, and hence the incorporation of technology is never neutral. Technology has been able to thrive within the capitalist context due to its objective nature that allows for rationalized development. While technology in its pure form exists as an abstraction and could potentially remain neutral, its application automatically takes on socially and historically specific domains. The contradictory development of physical materials and digital geometries showcases the social prejudice incurred by the incorporation of technology, despite it behaving seemingly objective at a microscale. It therefore invites an evaluation of technology through its relationship with materials to explore the social domains that it influences. In every build project, opposing trajectories of physical materials and digital geometries must somehow converge through compromission of form or intensification of construction processes. By comparing the intended architectural experience and the chosen method of construction, the material outcome becomes representative of the relationship between the architect and the constructor. To understand the spectrum of perceptions that could be attributed to a singular material, we can follow the conscription of glass in modern architecture. In architecture, glass is used to pursue its linguistic narratives, such as in elusive force in Rowe and Slutsky's seminal essay, Transparency, Literal and Phenomenal, or as an honest material in modern architecture, free of ornamentation, as seen in Miss Vandero's body of work. In engineering, glass is deployed for its structural ideals, able to be quickly fabricated and constructed as observed in the Crystal Palace, and able to manage dynamic loads through its flexibility as demonstrated in the glass facade of the City of Science in Paris. The multiple ontological understanding of glass reinvestigates the shortcomings of digital geometries and the consequences of employing monological accounts of material in the digital environment. The convergence of opposing trajectories and the incumbent relationship between architects and constructors can be observed in the development of the glass sails in Frank Gehry's Fondation Louis Vuitton. Taking inspiration from the sails of the 1911 J-class yacht Suzanne, the expressive glass sails of the Foundation adds to the archival of bizarre forms designed by Frank Gehry. The firm was interestingly positioned in contemporary architecture practice. On one hand, Gehry himself is famously known for conceiving extravagant forms using traditional model making. Yet, Gehry and Partners is recognized for being at the forefront of the AEC industry with their own BIM software digital projects, which is created under their research and computation subsidiary Gehry Technologies. This unexpected synthesis between highly dexterous and computational processes were intentionally engaged to enable Gehry's formulative designs to bypass the Euclidean domination that systematized formulation and fabrication production. But the Euclidean syntax aligns much of our fabrication industry, and to veer away from it will demand unconventional or manually laborious building techniques. This framework clearly prioritizes imaginative formulations and disregards the reality of resource intensity, using digital geometries to justify such bizarre forms to be achievable. The resultant construction implication of non-Euclidean geometry in Gehry's architecture is discussed in Dennis Sheldon's doctoral dissertation, Digital Surface Representation and the Constructability of Gehry's Architecture. The co-founder of Gehry Technologies rationalizes that the physical modeling process was not solely a visual representation, but was imperative in the formulation process to stand in for those of craftsmen and fabricators on the resulting building construction. A statement of modeling material, which were directly converted to digital geometries, were thoughtlessly equated with physical materials, one to be representative of the other, believed to encapsulate consistent meaning across each stage of development. The architects did not acknowledge the digital geometries employed are fundamentally decoys that transfers liabilities from architects to the manufacturers and contractors. It oversimplifies material behavior and undermines the laborious aspects of craftsmanship. Following the formulation of these digital geometries, the chosen fabrication method is dependent on cost. Here, there are three options that the firm could take to manage costs. First is the rationalization of building form into geometric regularities to streamline production through accessible fabrication machines that operate Euclidean denomination. Second is to generate each component to be fabricated as discrete elements. This of course incurs higher costs with the state-of-the-art CNC fabrication machines that can handle freeform geometries effortlessly. The last option depends on the craftsman working on the component to figure out aspects of the component's configuration. This will enable the most cost savings, but will also require an increase in material usage to allow for structural buffers that these craftsmen could work with. The project team must therefore balance between the three methods to keep within the considerations of financial costs and at the same time achieve as closely as possible the desired form of the project. Across the three options, it should be noted that the component assembly is still dependent on manual labor, even if discrete elements could be fabricated using CNC machines. Understanding the realities of manual assembly, the extensive volume of 3,500 custom curved glass panels, 19,000 CNC cut custom ductile mounts, and its respective customized hanging hardware in the construction of Foundation Louis Vuitton could possibly explain the cost of the project exceeding its original budget by nearly 8 times. Equating physical model-making materials with physical construction material becomes problematic as the project was conceived with a lack of prior understanding regarding material behavior. Without fundamental material understandings, what does the skills of a craftsman mean? It becomes a loose term exploited to hide the relegation of complex fabrication procedures to extensive manual labor, as these subjective values are difficult to account for within digital geometries. Nonetheless, the domination by the trajectory of digital geometries within the materialization of the project expanded the material qualities of the original physical material. Its disregard for feasibility challenges the conventional standards associated with glass within the fabrication industry. Instead of accepting the conventional building float glass to be uniform, flat, and fragile, the project contended with the use of curved glass in automobiles and recognized glass to be dynamic, malleable, and invigorated, able to mimic the visual motif of moving cells. The convergence of physical materials with digital geometries in this context leaned onto the trajectory of digital geometries, successfully conceiving its intended form at a high price of resource intensity. Of course, such endeavor was made possible by access to the patronage of Foundation Louis Vuitton, who were eager to realize an iconic building for the French luxury fashion house. Granted with adequate authority, the unbounded nature of digital geometries, able to be encoded as desired, enables it to disrupt the dormant cost of physical materials within the fabrication industry and induce points of innovation in its operations. To understand the extent of materiality associated with physical material and digital geometries of glass, we need to investigate the tray of tools adopted by each profession across the supply chain until the installation of the glass components. Tools systematize the process of humans working with materials, and the design of a tool suggests the material's behavior that it was intended to deal with. Comparing the tools used in formulation and fabrication processes identifies the differences between physical materials and digital geometries. Tools encapsulate instrumental knowledge within its mechanical or procedural operations. The execution of tools reduces the necessary knowledge to replicate the processes of these tools manually. Reliance on tools, coupled with an incomplete understanding of its processes, creates ruptures in the knowledge system of material production. We do not know how it works, but we trust that it works. This truncated understanding of material behavior does not allow for knowledge gain to be conveyed across the production workflow. Without a shared understanding of material behavior, the conflation of physical materials and digital geometries therefore results in either an overassumption of material capabilities or an undermining of material behavior. Fundamental knowledge regarding material behavior will be necessary to push the boundaries of the material feasibly without resorting to conventional building methods or ignorantly fantasizing resource-intensive formulations. Today's tools are no longer purely mechanical, but also programmed into computational systems. Much of the operations available in the digital environments are tools pre-programmed into the software system and can be integrated as desired. Digital tools encapsulate certain procedural knowledge that draws influence from the industry it originated from. One of the earliest digital environments, Kasia, was developed by Dassault Systems, an in-house system of Dassault Aviation. Naturally, the operations of Kasia were intended for aircraft design. The splines and fluid forms that we observe in architecture were conventionally designed for the aerodynamic forms of planes. Though the splines and freeform curvatures can be applied across industries, it was originally programmed to fit the fabrication workflow of the aviation industry. The complex splines of aircraft manufacturing can be easily molded on the steel panels it was intended for. Manufacturing costs could also be reduced by replicating the product numerous times to cover initial costs in economies of scale. In the context of architecture, resultant digital geometries of similar curvatures are difficult to produce with many materials. Selected building techniques, such as the curtain wall system that complement free-form curvatures, are favored as a result of digital design resolution. These tools therefore do not always encapsulate the most appropriate knowledge required for architecture and construction. Understanding that the epistemological logic of digital geometries varies in various digital environments, it becomes necessary to surface specific information unique to the built industry. Depending on the digital environment, the various information encoded in digital geometry therefore differs according to its purpose. Meshes intended in 3D files can be conveniently 3D printed, but cannot replicate similar levels of properties in IFC domains. Rhinoceros files, originally meant for computer graphics, have a mesh-based malleability that does not need to be translated into physical materials. Conversely, BIM software using IFC is fundamentally dependent on the physical materials that it is attached to, based on the material catalog available in the current industry. Differences in the programming of digital environments further increases ruptures in the knowledge system. Considering the above, there are two perceptions of materials that alter the synergistic conditions of the construction industry. Working with digital geometries and being able to encode information in them successfully detaches material from conventional notions and enables designers to generate new forms. The potential risk that such workflow creates is the further conflation and detachment of the architect from the realities of construction, blindly generating intensive resource allocation in construction procedures that further burdens the construction industry. However, deliberately restricting designers to work from a palette of available physical materials and building techniques, as seen in Giles Fredsin and Molly Claypool's discrete architecture, would create a limitation to form expression that impedes the creativity of a designer. How do we provide a balanced framework for the construction industry such that it progresses across stages optimally without becoming sterile or unempathizing? Unlike tools assigned to individual processes, materials are malleable and able to proliferate throughout manufacturing and construction processes. A plausible hybridization of physical materials and digital geometry could mitigate existing ruptures in the knowledge system by employing the agency of materials. Digital geometries must be encoded with tactile experiences of physical materials, its tolerances and affordances that can be accessed through an external haptic device to increase accountability. Physical materials must be reimagined to embody new material behavior to induce new forms of construction through digital geometries. Cross-pollination between physical material and digital geometries provide a form of system without resorting to standardization, enabling the industry to mutually progress. To account for the material affordances in digital geometries, tactile material behaviors have to be translated into an encodable binary format in order to permeate into the digital environment. The creation of encoded materials using digital geometries encoded with tangible material behavior creates a hybrid intersection between physical materials and digital geometries made accessible through an external haptic device. Through encoding material behavior derived from physical materials into digital geometries, the encoding restructures an understanding of materials to perform consistently between both the digital and physical domains. It allows for the architect to be able to interact with tangible material behavior while working in the digital environment. By synchronizing material behavior into the digital environment, digital geometries can no longer be perceived as dull matter, but one that embodies its own behaviors and affordances, responsive to the splicing and stretching by the architect. The interdependency generated between digital geometries and physical materials no longer allows for further disengagement between stages. Digital geometries encoded with existing material properties will recenter a more empathetic perception of material behavior and reduce resource intensity in construction practices. Anonymous materials encoded with non-existent material properties will clearly identify areas that require innovation intervention from material and structural engineers without relegating the liability of unrealistic designs to manufacturers and contractors. Through this synthesis, the more fluid process allows for a return of the digital master builder who designs and builds with encoded materials.